All right. Well, hello, good morning, everybody. I hope you're having a nice week. Welcome to those of you in Marcus and those of you joining on the live stream. A couple quick announcements before we get started. So I sent an email out this morning. There's going to be a review session tonight from 5 to 6, as well as Monday from 4 to 5, reviewing critical points and inflection points. So if you're looking for more practice on those concepts and ideas, definitely feel free to attend those. They will be the same tonight and Monday, so you would pick one. It'll be really helpful for you to really have mastered those sorts of ideas before next week, when we will be applying those to look at applications of local maxes, local mins, inflection points to both business as well as biology and chemistry. So next week we'll be doing all applications. Additionally, I sent an email regarding how you can calculate your current average. Because the average changes every time you submit another assignment, this calculation only works for this week. So if you're interested in what your average is, definitely check that out and calculate it before next week's work starts. So yeah. So those are the announcements. We are moving into section 4.3, which is called global maximums and minimums, which we alluded to back when we talked about local maximums and minimums, but now we will learn about them formally, what they are, how we find them, and all those sorts of things. So I'm going to switch over to the dot cam. Okay. And before we talk about the definition, I want us to look at this picture and just remember what we've learned about local maximums and minimums, so we can tie it in and see the difference between a local and a global. So as a reminder, we are going to have local minimums whenever we are at the lowest point in a small area. And we are going to have local maximums whenever we are at the highest point in a small area. And the way that we found these points was by finding critical points, which is when the first derivative equals 0 or is undefined. And that would give us the x value to tell us where to locate these. Okay. So today we're talking about something called global maximums and minimums. This is also referred to as absolute maximums and minimums in math. So you might hear that wording. So global and absolute mean the same thing. So a global maximum, a function is said to have a global maximum at some point p if f of p is greater than or equal to all the values of f of x. So what does that mean? That means you're going to have a global max if you have a point on your function that is bigger, and when I say bigger, I mean higher on the y scale than all the other points on the graph, right? So if we look at the picture that we have here, and we look at all the points, is there a point that's the highest? Yep, it's right here. So this is going to be our global maximum. And the global maximum is the y value, because we're talking about comparing higher points and lower points. So we want to know what the y value is. So the global maximum here is 2. Okay. A function is said to have a global minimum at p if f of p is less than or equal to all values of f of x. So again, we're going to look at our function and we're going to say, is there a lowest point? Well, yes, it's right here. So our global minimum, so that's going to be the y value at approximately 0.5. Okay. Some things I want you to notice. When we talk about the global max and global min, we define them by their dependent value, so the y value. Functions will only have 1 or 0 global maxes or mins. You can't have 2, because if you have 2, then one of them has to be bigger, right? If you tell me that the highest y value is 4, then it cannot also be 5, right? So there can only be 1 or 0. However, the global maximum can happen at many places, and I'll show you a picture of that in a minute. I want to highlight here, however, that over in this particular point, that this point is both a global and local minimum. Okay, so it can do both. So that's going to be important for our work later. But let's go back to this point here. Functions have one or no global maxes and mins, and they can happen at multiple places. So we have a situation here where we have one global maximum and one global minimum. What would it look like if we had no global maximum, right? So if we have no global maximum, we might have a function like x squared that goes on and on forever that looks like this. This function has a global minimum. It has one lowest point, but it has 0 global maximums because these arrows indicate that this function goes on forever. So there's no highest value. Okay, what about these things happening at multiple places? What does that mean? Well, let's say we have a function that -1, -2, 1, 2. Let's say we have a function that looks like this, right? So make this a little more exaggerated up here. So we don't have the arrows, so we don't worry about going off forever. So the global maximum is whatever this y value is here. So let's say that's like 2.5. But when we talk about the global minimum, let's assume that these are at the same point for the sake of the exercise. We see that these both happen global minimum at negative, or the global minimum is -2, but it happens at 2 different places, right? It happens here and here. So it can happen at multiple places, but there's only one minimum because we define that by the y value, right? So we could actually just like have a function that kept hitting that same global minimum again and again at -2, and that's fine because there's only one global minimum value. So there's only one global minimum, it's -2, but it happens at multiple places. So that's what that means. Now, when we are trying to determine global maximums and global minimums, they can only happen at 2 places, okay? The first place that they could happen is at a critical point. So we see here, we see here and here, we see here that these global points are at critical points because they are places where we also have local points, right? Where we have these horizontal tangent lines. The other place that they can happen is at an endpoint. So we see that here and here. If your function has endpoints, the global function could also happen there, right? So the global max could be at an endpoint or a critical point. So we have 2 cases that we look at when we talk about global maximums and minimums. The more common case is when we have some sort of endpoints, whether algebraically or on a graph or conceptually. So we're going to talk about the ones that have endpoints first, and then we'll do an example at the end where we don't have endpoints. So the summary here is that in order to find global maximums and minimums on an interval that has endpoints, we compare values of the function at critical points and endpoints. The highest value from that list is the global maximum, and the lowest value is the global minimum, okay? So we'll come back to the definition of what to do without endpoints later, but let's talk about what this looks like in practice. So this is what a common problem is going to look like. Find the global maximum and minimum of the function x cubed minus 9x squared minus 48x plus 52 on the interval -5 to 11. So when you have this interval, those are your endpoints. So the process is that we make a list of critical points and endpoints. Well, the endpoints are given in the problem, right? So they're -5 and 11. So we can just write those down to start with. -5 and 11. However, we don't have the critical point yet. So the process will be that we will find the first derivative, set it equal to 0 to find the critical points. We will add those critical points to our list. Once we have our list of places where the global max or min could be, we plug all of these x values in one at a time into the original function to get the corresponding y values. Then we look at those y values, that list. The largest y value is our global max, and the lowest y value is our global min. So I'm going to have you try this. So again, you're going to find critical points the way we've been finding critical points the past week or two. You're going to add them to your list. Then we're going to plug all those points into the original, get the y values, and figure out what is the biggest and lowest y value. So this is the first time we're doing this one, so I'm going to give you about 3 minutes just to sort of sort it all out as you go, try it all out, see what you can figure out, and then we will go through it together. Okay, take about 30 more seconds. All right. So we have our endpoints given in the problem. And now we need to find the critical points to add to this list. So we find the first derivative of our function, which is going to be 3x squared minus 18x minus 48. We want to know, when does that equal 0? Okay. As I've mentioned before, there's a lot of different ways you can approach it from this point. It's a matter of preference. I like to factor. So I factored this out, and I get 3 times x minus 8, x plus 2. So I factored the 3 out first, and I was left with a function that I could then factor further. So my critical points here are x equals 8 and x equals -2. I have to do a step in between finding the critical points and adding them to my list. I need to make sure that my critical points are on the interval that I am considering. So I can only consider X values that are between -5 and 11. So if any of my critical points are not on that interval, I would not include them. Fortunately, both of my critical points are on this interval, so I add them to my list. So I have X equals 8, X equals -2. Those are my critical points. So I have a list that includes endpoints and critical points. Once I have my list, I'm going to plug each one of these back into the original function to get the corresponding y value. So when I plug a -5 into the original function, I get -58. When I plug an 11 into the original function, I get -234. When I plug in an 8, I get -396. And when I plug in -2, I get 104. And obviously I'm plugging those on my calculator, not in my brain. That would take a lot of time for me. So I plugged each one in through my calculator, and these are the corresponding y values that I got. So once I have those y values, now I can make a determination about my global maximum and my global minimum. So I'm going to look at my list and I'm going to find the number that is the highest on a vertical number line, right? So positive numbers are going to be higher on the number line than negative numbers. So the largest value here is going to be 104. So my global maximum is 104, okay? To find my global minimum, I'm looking for the one that's going to be the lowest on the number line, which in this case will be the most negative number, since I have negative numbers. And I see that -396 is going to be the lowest on the number line. So I'm going to just write this up here for space. My global minimum equals -396. So one of the things I have to be extra careful about is what the question is actually asking me to report. So here it was find the global maximum and minimum. Great. That's the y values. Okay, I'm going to report them just like this. I would say the global minimum is -396. The global maximum is 104. Sometimes questions are worded in such a way that you need to find the global max and min, but then answer the question about where it happens, right? So it may happen, at x equals negative or x equals 8. So you have to be careful about the wording, whether you're finding the global max and min, like we did here, or you're answering some sort of related question. We'll sort of practice this in the next couple to make sure that we understand how to answer the question that's being asked. But the process here, again, is that we need endpoints and critical points. We put them in a list. We plug each of those into the original function. Then we compare the dependent values to see which one is the largest and which one is the smallest. So let's try another one here. So the number H of eggs hatched by a specific insect at a given temperature T in degrees Celsius is given by H of T equals 2T cubed minus 45T squared plus 264T, where T is between 3 and 15. Find the temperature at which the largest number of eggs hatches. So again, the temperature here is in Celsius. So we're talking about between 3 and 15 degrees Celsius. We have the two endpoints, 3 and 15. We also need to find the critical points by setting the first derivative of this function equal to 0. Once we have our list, we will plug those values into the original function to find the largest number of eggs hatched, our global max. And then we answer the question, what is the temperature for which the largest number of eggs are hatched? So then we have to go back and find the corresponding T value. Okay, so we need about 3 minutes, try it out, see what you can figure out, see how far you can get, and then we will go through it together. Okay, take about 30 more seconds. Okay. So again, we need critical points and endpoints. We have our endpoints here. So we have t equals 3 and t equals 15. So that starts our list. Now to find our critical points, we need to set the first derivative equal to 0. So my first derivative here, I will have 6t squared minus 90t plus 264. I'm going to factor this. If you don't like to factor, you can use the quadratic equation. That's totally fine. I'm going to pull out a 6. So I'm left with t squared minus 15t plus 44. So I, on my calculator, made sure that all of these numbers were divisible by 6 so that I could pull it out. So now I'm looking for two numbers that multiply to give me 44, but add up to give me 15. So I get t minus 11 and t minus 4. Okay, so that means my critical points are t equals 11 and t equals 4. So again, I need to check and make sure that these are on my interval. So my interval is 3 to 15. Great. So I get t equals 4, t equals 11. I can add them to my list. So now I need to go ahead and plug all of these temperatures back into the original function to see how many eggs are hatched for each of these 4 temperatures. So when I plug in a 3, again, into the original function, I get 441. When I plug in a 15, I get 585. When I plug in a 4, I get 464. And when I plug in 11, I get 121. Okay. This all seems really good to me because these are positive numbers. I'm expecting these to be positive numbers. If they weren't, I would be a little concerned given the context. But I look at these and I say, okay, I'm looking for the largest number of eggs hatched. So that is a global maximum. So in this list, the largest number of eggs hatched is 585. So if the question was, what is the largest number of eggs hatched? I would be reporting the global maximum of 585. But the question is find the temperature at which the largest number of eggs are hatched. So I need to then go and find out what was the temperature that gave me the largest number of eggs hatched. So here, to answer this question, the temperature that led to the global maximum was 15 degrees Celsius. Okay, so again, we just need to be careful that we're answering the question that is asked after we apply our process. Okay, so let's look at one more that's a little bit, I'm not going to say more difficult, but a little bit more, we have to be a little bit more careful on taking the derivative because for this particular function, in order to find the global maximum, we have to do a quotient rule, right? So here we have the function x over x squared plus 1, and we want to look at it over the interval 0 to 2. And we are looking for the global maximum. Okay, so we already know that 0 and that 2 are going to be on our list because those are our endpoints. So we need to find any critical points by looking at where the first derivative is 0 or undefined. We will add those to our list if they are on our interval. We will then plug those back in to get the corresponding y value or g of x value. Then we will look at those to see which one is the biggest, and that will be our global maximum. Okay, so take 3 minutes, try this out, and then we will go through it together. Okay, take about 30 more seconds. All right. So to find the critical points of this function, we have to do a quotient rule because we have one function over another one. So we set up that our top function we call f, our bottom function we call g, and then we need to find each of their respective derivatives. So the derivative of x is 1, and the derivative of x squared is 2x, and the derivative of the 1 by itself is 0. So when we plug this back into the quotient rule, we have f prime times g. So we have 1 times x squared plus 1 minus g prime times f. So 2x times x is going to be 2x squared, all divided by g squared. So we have x squared plus 1 squared. We want to simplify this so we can work with it. So we have x squared minus 2x squared and then a plus 1. So we can write this as 1 minus x squared over x squared plus 1 squared. So as a reminder, when we have something like a quotient rule, we do have to consider the undefined case. So the way we work with quotients is that we set the numerator equal to 0 to find critical points when the function equals 0. And we set the denominator equal to 0 to find anything that's undefined. The denominator here, however, does not have any solution that would make that equal to 0 because this is a squared number. So the only thing that would make this 0 is if x squared equaled -1, which we know can't happen. So that means we only need to worry about the numerator here. So we have 1 minus x squared equals 0. We're going to bring the x squared over to the right. We're going to add that over. So we have 1 equals x squared. So when we solve that, we take the square root of both sides and we get x equals 1 or x equals -1. Okay, is the solution to this. So we have two possible points that are critical points. And so we need to determine if we can add them to our list. So we go back to our interval, and the interval is x has to be between 0 and 2. So that means that x equals -1 cannot be put on our list because it's not on the interval, so we can't consider it. So we are only going to add x equals 1. Okay, so make sure that you check all your critical points and only include the ones that are on the interval. So now we have our list. We want to plug each of these points back into the original function. So if we take 0 and plug it in, we get 0 over 0 plus 1. So 0 divided by 1 is 0. When we plug in a 2, we have 2 on the numerator and then 2 squared plus 1 on the denominator. So that's 2/5. And then when we plug in a 1, we have a 1 in the numerator and then a 1 plus 1, which is 2 in the denominator. So we have 0, 2/5, and 1/2. And in this particular problem, we're looking for the global maximum. So we're looking for the largest value. So the largest value from this list is 1/2. If you have trouble comparing fractions, you can convert them to decimals to compare if that's easier for you. So here we have 1/2 is the largest value on this number line. So 1/2 is the global maximum of this function. So the answer to this is 1/2. Okay. So again, the wording is really important. If this was on a mini quiz and it said, find the global maximum, the answers would likely be something like A, 2, B, 1, C, 1/2, D, 2/5. Okay, something like that. And so 1/2 is the global maximum. but a lot of students will pick 1 because they're reporting the X value. And so it's really important that you understand the distinction that the global maximum and minimum of a function is the Y value. Okay, there are times when we ask for the independent value and it's worded like this, but you really have to read the question carefully and make sure you're reporting the right information. Okay, so let's look at how else we might sort of analyze and think about information related to this and see if we can put it all together to sort of sort through information and understand how things interact. Okay, so let g of x be a continuous function that has exactly 1 critical point on the interval -3 to -2. Find the x values. So again, we're looking for x values here, which is slightly different, at which the global maximums and global minimums occur on this interval, given that g prime of -2 equals 0 and g double prime at -2 equals 3. So I want you to take 2 minutes, think about all the information you are given in this problem and what it tells you. So start by saying, what does this information tell me? And then think about how that might help us answer this question. It may be helpful to try to graph it. It's up to you, but take 2 minutes and see what you can work through for this set of information. Okay, take about 30 more seconds. All right. So what is the important information here and what does it tell us? Okay, so we have a function that has exactly 1 critical point. So that's going to be helpful to us. We also know that g prime of -2 equals 0. Well, by definition, if the derivative at some value equals 0, that is a critical point. So the exactly 1 critical point happens at -2, right? Because that's on our interval. We also know that the second derivative at -2 is 3. Remember, the second derivative tells us about the concavity of the function. So this tells us that we are concave up at that point. That also tells us that our critical point is a local minimum. Okay, in order for it to be a local minimum, it's going to be lower than all of the points around it. So when we think about graphing this function, okay, we know that we're going to have something that roughly looks like this, right? And the rest of the function might look like this, but we're not considering what's happening later. So when we think about the concavity of the function, paired with the fact that this is a local minimum, that helps us realize where the global maximum and minimum need to happen. So we have a global minimum at x equals -2, and we have a global maximum at x equals -3, okay? And so you may think, well, how do we know that there's not other things happening between -3 and -2? So let's explore some alternatives that we think could happen and see if they're realistic. So one thing that we might be worried about is that there's all sorts of wacky things happening where this is a minimum, but then it looks like this, right? How do we know that the global maximum happens at -3? Well, the reason I know that the function cannot look like this is because if it did, look what happened. There's a whole bunch of critical points, right? In order for it to fluctuate up and down and turn around, that creates critical points. And we know that there's exactly one critical point, which means I can't turn around between -2 and 3, because if I do, it creates new critical points. The other thing that could happen is I could have a change in concavity, right? I know that I'm concave up at -2, but what if I was concave down before that, right? Like what if I have something that looks like this? Well, that's fine. That doesn't change our answer, right? So here, there's still only one critical point here. So maybe this is a little more sharp. As we go up, we haven't quite reached the critical point yet. There's still only one critical point, but -2 is still where the global minimum happens, and -3 is still where the global maximum happens. So we could, in theory, have a function that does change concavity, right? But it doesn't change the solution. Additionally, we don't know where this lives in space. So this could be like down here, right? That's fine, but it still doesn't change the outcome that the global minimum's at -2 and that the global maximum's at -3. So any graph that you are able to draw that satisfies that we only have one critical point, that we're concave up at -2, and that this critical point is a local minimum, will result in an end result that the global minimum has to happen at x equals -2, and that a global maximum is going to have to happen at -3. Okay, so trying to graph some different scenarios always helps me sort of figure out what's happening. So hopefully that helps you understand why that must be true. So the next bit of analysis we're going to do is we're going to evaluate a graph, but we're going to look at it on different intervals within the graph. So we're still looking for global maximums and minimums, but we have 3 cases here where we have 3 different intervals related to this particular picture, okay? So for part A, we have -1 to 1.5, so that's the entire interval. We're looking for the global max and the global min, which again are the y values. For part B, we're only considering what's happening between 0 and 1. So we have to shrink that interval. And for part C, we're looking between -0.5 and 0.5. So we're looking at different parts of the function for each of the different scenarios. So I'd like you to take 2 minutes, look at each of these intervals and try to approximate the global maximum and global minimum for each of the given intervals, and then we will go through it together. Okay, take about 30 more seconds. All right. So for interval A, which is the entire interval, we are looking for the highest and lowest point on the graph as it's given. So I notice that the highest point is just about here. And I come over until I hit the axis, and then I have to approximate what that y value is. So I'm going to approximate my global max to be, I don't know, 1.6, right? Yours might be 1.7, 1.75, but somewhere in that general range. And then my lowest point is way over here at this endpoint, right? And so I see that it's exactly where I hit the axis. So my global min, right, is going to be right at 0. So again, right, global max and min happen at endpoints or critical points. I can see that this is a critical point. Okay, so that all combines with what I already know. So now when I look at interval B, I'm looking between 0 and 1. So I go up to 0 and I go up to 1. And I kind of just sort of trace the interval between them. And so now I'm just looking between these two dots. And so I notice that my global max, right, on this interval is at 1. It happens in two different places. It happens at both 0 and 1, but the global max value is 1. And then my global min happens at this little dip, right at the bottom of the dip. That's going to create a critical point. And so I'm approximating the y value here. So if I look at this between 0 and 1, I'm going to call that something like 0.8, right? You might call it 0.75, 0.9, somewhere in that general range, okay? But again, I'm only looking at the values on this interval. So then finally, for part B, or for part C, excuse me, I'm looking between negative 0.5 and positive 0.5. So if I go here, let's see, about halfway between, I'm going to draw this sort of straight up and down to create my interval. So I'm looking between these two lines. So I'm looking at this part of the function right here, right? And so what I notice is that my 0.5 hits just about where this was before, right? So my global maximum value happens at what is now an endpoint, but used to be a critical point before I put in my interval. And that, I said again, is approximately 1.6, right? Based on that y value. And my global min happens just about here, which is where I had my local min before on my previous interval. And so I said that's approximately 0.8. Okay. So when you have a graph and you want to talk about global maxes and mins, you do need to consider if you are given some sort of interval to consider, and then make sure you're only looking between those points. Okay. So that's what it looks like on a graph. So those are all examples that include endpoints in some way, shape, or form. And like I mentioned, the majority of problems you will do will have endpoints included in some way. So you'll be given an interval, or we see here the endpoints are -3 and -2 based on the brackets. And so we have to consider the other case where we don't have an endpoint. So I'm just going to go back to our definition page that we started with. So what do we do if we don't have endpoints, right? So in order to find a global max and min on an interval that doesn't have any endpoints, so just an open interval, we compute the values of the functions and find all the critical points. So we still do that step. We say, okay, are there critical points of this function? And when we do that, there's a couple things that can happen, okay? If there's multiple critical points, so more than one, we are going to use a picture. So we're going to graph the function to figure out if those critical points are global maximums or minimums. So why would we do that? So let's say, for an example, we have a function that looks like this. Okay, so no endpoints, just goes on forever and ever. We have 3 critical points here, right? So we have 1, 2, 3, but only one of them is global, right? So this is a global minimum, and there is no global maximum because these go on forever and ever. So we didn't have endpoints. We had 3 critical points. We had to figure out, are any of them global? And the easiest way to do this is with a picture. Okay, so that's what happens if you have multiple critical points. If there's only one critical point, then that critical point is either going to be a global max or a global min, or in some rare cases, it could be neither. And so what we do is we take that one critical point and we use one of the tests to determine, is it, global max, global min, neither. And in the case of one critical point, if it is global, then it is also local. So what does that mean? So one critical point, you might have something like this. Okay, so this is a global max, but it's also a local max. Okay, so if there's one critical point, you can use the test that we had before to figure out, is it a max or a min, right? If we had something that was sort of the opposite, right? We have a global min, also a local min, right? In the weird case that it's neither, right? It's going to be flatten out, look like this. And so if we use one of our tests from before, we would still get neither. So if there's only one critical point, you can use all of the tests that we used before for local max and mins to figure out whether it's a local max or min, and it will also be the global max or min. Okay. The other and easier way I think to do this is to graph the original function, right? If there's one critical point and you graph it, you can see pretty clearly if it's a global max, global min. But in the case of one critical point, if it is a global max or a global min, it will also be a local max or a local min. So again, this type of problem doesn't come up as often just because it's a little more vague in how we do it. But we will do one regardless, just so we can see how this works. Okay, so here's the problem we're going to do. You'll find that when we do have this case, the algebra tends to be a little more aggressive is not the right word, a little more, I don't want to say difficult, that's not the right word either, but it's more involved, okay? So for a time t greater than or equal to 0 in days, the rate at which photosynthesis takes place in the leaf of a plant, represented by the rate at which oxygen is produced, is approximated by, and we have this function, P of t equals 100 times e to the negative 0.02 t minus e to the negative 0.1 t. It's 2 questions. When is the photosynthesis occurring fastest? And what is that rate? So we're looking for the global maximum in the situation. The global maximum is the rate, because that's what the P is. But we also want to know the corresponding T value that gives us that fast rate. So we don't have endpoints here. We do have that this has to be greater than or equal to 0. So it's kind of like a bottom endpoint, but we expect that whatever the critical point is will be our maximum, right? That makes sense in this context. So we need to find the first derivative. We need to find the critical point. Once we have the critical point, we need to plug it back in. And then our critical point, which is a T value, is the when. And when we plug it back into the P and get the P value, that is the rate. Okay, so to find the critical point here, we do have to do some interesting algebra once we found the derivative. So I'm going to have you try this. I'm going to give you about 3.5 minutes to try out the algebra. But take the first derivative of this function, then we're going to set it equal to 0, and we're going to try to solve for t. And the one sort of, I guess the two sort of hints I'll give you is that in order to solve for t, once we're at that step, we need to figure out a way to simplify our function into only having one t value. If you get to the first derivative and you can't figure out how to do it when it's set equal to 0, I encourage you to try graphing the original function on your calculator to see if you can figure out approximately where the maximum is as an alternative to doing it algebraically. Okay, so take about 3.5 minutes, try it out, and then we will go through it together. Okay, take about 30 more seconds. All right. So we have our original function and we want to take the first derivative. So we have the 100 that's in front, that's a constant multiple. So that will multiply our derivative. And for each of the e terms, the constant is going to come out in front. Okay, we have to be a little bit careful with the second term because the negative 0.1 is going to come out and we have a minus here. So I took an extra step to simplify by just taking the minus and the negative and making that a plus. So our first derivative should look something like this. Okay, so hopefully you were able to get that. And then we have two factors multiplied together equals 0. We know that 100 doesn't ever equal 0. So we take what's in the parenthesis and set that equal to 0. So that's all the derivative work. So hopefully, you're comfortable with that. You do have to be extra careful with the negatives and the decimals, but that's sort of the calculus part of this to get it now reduced down to an algebra problem that we need to solve. So to solve the next part, we're trying to solve for t. And what I notice is that my terms have different powers. So I can't combine these together, right? If they had the same power, then I could just combine the constants, but they don't. So the way that we approach this at this point is we need to figure out a way to get it so that we only have one t. Because if we only have one t, then we can use natural logs to solve. There is a way to use natural logs prior to this, but it's a pretty complicated set of algebraic steps. If you did it that way and you were able to successfully do that, that's fine. But I would encourage you to think about trying to simplify first. So in order to combine these, I'm going to have to consider them in a ratio. So in order to do that, I need to bring one of these terms to the other side. It doesn't matter which one you bring over, but I'm going to pick the first term so that both terms end up being positive, right? So I'm going to bring this over here. So then I'm left with 0.1 e to the negative 0.1 t equals 0.02 e to the negative 0.02 t. So I just brought this over, I added it to both sides, and now I have something that looks like this. So there's two parts to each term, okay? There's the constant that's in front, and then there's the e term. And so what I want to do is I want to get the constants together and the e terms together. So to get the constants together, I'm going to divide both sides by 0.02. You can divide both sides by 0.1. Instead, you will still arrive at the same answer eventually. This one just works out a little nicer if you divide this way. So we get a 1 on this side, and 1 times anything is just itself. And then on the left, if you do this on your calculator, if you do 0.1 divided by 0.02, that is actually 5, right? So that's a nice simplification here. So we have 5 times e to the negative 0.1 t equals e to the negative 0.02 t. So now I also want to combine the e terms. And so I'm going to divide this one over here so that I have a constant on one side and my e's on the other side. And again, it doesn't, like if you had divided by negative or by 0.1, then you would divide by this e term so that all the e's are on one side and all the constants are on the other side. Okay, on the left, again, this creates a 1. It's a ratio of 1. That will always be 1. And then on the right is where we have to do some of our work. So we just have a 5 on the left. Now let's look at what's on the right. This is where one of our algebra definitions comes in. If you have two terms with the same base, right, which we have here, e is our base, we can subtract their powers. So we often do this with x's, right? If you have x to the 6th over x to the 4th, that just gives you x squared. Well, why? Because you have 6 x's multiplied together up here, 4 down here, and we cancel 4 of them off to make 1s, and you're left with an x squared. The generalized rule is that we do 6 minus 4, right? We subtract the powers, top power minus bottom power, because they have the same base. We can do the same thing here. We can simplify this by subtracting the top power minus the bottom power into a single power. But what is that power? We have to be really, really careful with this calculation. So I'm actually going to do it over here on the side. So we have negative 0.02t, that's the top power, minus negative 0.1t. That's the one down here, okay? Since this is minus a negative, that becomes plus. So we have 0.1 minus 0.02. So that leaves us with 0.08t, okay? So we have e to the 0.08t, e to the 0.08t. Okay, so that's the simplification of this. And now that we have that down to only having one term with t in it, we can take natural logs. So we take the natural log of both sides. So we get the natural log of 5 equals the natural log of e to the 0.08t. We use our natural log rules, so we know the power comes down out front times the ln of e. Okay, so the power comes down. The natural log of e is just 1. So to solve for t, we divide both sides by 0.08. So we have t equals the natural log of 5 divided by 0.08. So this is an exact answer. Okay, we didn't round anything along the way. This is exactly when it happens. If we were to convert this into a decimal approximation, we would plug this into the calculator and we would get 20.11. So this is our decimal approximation. So what does this mean? So t was time and time was in days. So that means that the maximum rate happens after 20.11 days, okay? Days, 20.11 days is when this happens. So this is answer to the question when. And then we also want to know what is the rate. So we have to take that rate and plug it back into the original function. Okay, so we take 20.11 or the exact answer if we're looking for something exact. We come back up here, we plug it into the original function to answer the question, what is the rate? So when we plug that in, we get 53.499. Now, we don't have units on that rate. They were not given to us in the problem, so we don't need to worry about the units of the function. I want to mention that I said something to the effect of, if you didn't know how to do the algebra here, you should consider graphing the function. So if you got the derivative and you got stuck and you were like, I don't know how to do the algebra to finish this, if you were to graph the original function, right, you get something that looks like this. And so we see that the maximum, right, happens right about 20.1, which is what we found, right? So it's still in the general area. We can get a decent approximation. You can calculate a maximum on a calculator, and we can see it very clearly here. So you can see the x value and the corresponding y value. If we wanted to calculate the maximum, we would do second calc. And then here you'll see that one of the options is maximum, right? It wants a left bound, so we want to go somewhere to the left. It wants a right bound, so we want to go past it to the right. It wants a guess. It does this because there might be more than one, right? And then it'll calculate it for you. And you'll see we get the same thing that we got algebraically by using the graph. So you can always double check your work that way, or if you get really stuck on some sort of algebra, I encourage you to look at the picture to see if there's a way you can figure it out alternatively. Okay, so that's our last problem for today. We will pick up next week, like I said, with applications in business and in biology and chemistry using local and global maximums and minimums and inflection points. So make sure you feel very comfortable with these concepts for Tuesday so we can start applying them in practice to lots of different things. Okay, have a nice weekend, and I will see you guys all next week.
Does anyone have a question for the professor before I pack this